In this video, I'd like to introduce integration by parts and go over one example of applying this technique of integration. So first, I want to share with you a story that's going to go along with our entire integration unit that I've mentioned before, but is worth mentioning. The story of differentiation is a rather simple one. We learn 4 basic rules for how to take derivatives of functions, and it's a very straightforward process to complete taking the derivative of a function of a single variable. The picture for integration is much messier. So what we've been doing systematically is starting at the very beginning and trying some basic techniques of integration. The first that we learned was substitution, and the second that we're learning is integration by parts. So never fear, we're still at the start of this very messy process, and everything that's written down here below is not something we have to worry about yet. The reason that U substitutions and integration by parts are so high on this messy hierarchy of integration techniques is because they are somewhat of the opposite of some of our most basic rules of differentiation in their simplest form. So what a U substitution actually is an undoing of a basic chain rule. What we will see when we study integration by parts is that this is an undoing of a basic product rule. And because these integration techniques correspond so nicely with basic, simple, one-time applications of differentiation, they are fairly straightforward to apply and are good techniques to try to start with, as shown in this comical graphic. So let's see the way in which integration by parts is the opposite of the product rule. And in order to do that, I want to remind you of what the product rule is. It's a mechanism for taking 2 functions of a single variable, let's call that variable x, and our functions are u of x and v of x. If we take the product of those 2 functions and then wish to find the derivative of that product, we have to use the product rule, which I've rewritten right here. The derivative of the first function times the second function plus the first function times the derivative of the second function. Because finding antiderivatives, or taking integrals, is the opposite technique of taking derivatives, we can rewrite the process of taking a derivative, and we can reframe and think of this instead as how would I ask the same question in terms of antiderivatives? Well, what we would be asking for antiderivatives is, what function has this function over here as its derivative? And that would be written in this way. This original function is the antiderivative of the thing we see over here on the right. And we would put this antiderivative or integral symbol in front of this entire quantity, and we would be finding that antiderivative with respect to x. Now, in most of our integration problems, we are not given the sum of 2 functions inside of a single integral. Where we are going to see integration by parts is when we have the integral of a product of 2 functions. So to make this antiderivative statement look more like what we're used to being asked in a single integral problem, let's distribute that integral to both of the additive terms, which is just fine. Integrals work very nicely with respect to addition. We can distribute the integral in that way. And let's solve this equation so that we just have a simple antiderivative symbol with one of these 2 things on the right. And let's do that by moving one of the integrals over to the other side. And when we do that, we obtain this formula down here. The integral of u of x v prime of x dx is equal to u of x times v of x minus this other integral right here that we moved to the other side of the equation, u prime of x v of x dx. And this formula right here is the formula that's typically written down as the integration by parts formula. And what it's telling us is, should we encounter an integral that looks like the left-hand side of this equation, then the undoing of the product rule for this function is given by this formula.